Hey y'all, this is Doug Lauen, Associate Professor of Public Policy at UNC Chapel Hill. This is going to be a tutorial about regression analysis using Stata, and it's about how to interpret indicator variables, interactions, and how to graph things, graph predicted values in Stata. So I'm going to use the NLSY 08 data set, which is posted on the course website. That's the National Longitudinal Survey of Youth. The outcome is going to be income 08. The continuous predictor is math test score, and then we have two indicator, a categorical variable here, and a categorical variable here, and we're going to do some recoding to create some race ethnicity categories. So first I do some recoding. This isn't a tutorial about recoding, but I'm basically just getting rid of missing values here in a kind of crude way, not recommended, but this is what we're going to do for this tutorial. And then we're going to summarize the variables and create a categorical variable, a multinomial variable that has no order to it. It's just going to be white, non-Hispanic, black, non-Hispanic, and then Hispanic of any race. Okay, so I'm going to stop my code right here and just run it, and we can look at the output. Okay, so you can see, with my recoding, I'm taking whites who are non-Hispanic, blacks who are non-Hispanic, and then Hispanic of any race. And I'm creating a multinomial variable out of that. And then I'm creating indicator variables out of that multinomial variable, okay, called white, black, and Hispanic. Okay, so that just takes the indicator variable is coded 1 if yes, 0 if no. Okay, the reason I'm doing that is because we're going to use different types of variables in the regression to understand the mean differences. Okay, so what we're doing when we're running a regression with some indicator variables is we're just basically estimating mean differences in the outcome by those variables. So let's take a look at it. If we, without running a regression or anything, if we just table our results by our multinomial variable using Stata's table command, we go table, race ethnicity, which is the 3-category variable, and then we just ask for means of income and then the n of income. It'll spit out a table like this, and the way we interpret this is that white adults earned about $56,000 in 2008, and there were 2,000 of them in the data set. Blacks earned a lot less. The mean difference between blacks and whites is $17,000. The mean difference between blacks and Hispanics is only $19,000. And that's probably a misleading number. We're not using the weights in NLSY, so you wouldn't want to go. So as I said, we can show that the mean difference between whites and blacks is 17,462. The mean difference between blacks and Hispanics, whites and Hispanics, is about $1,900. So if we regress income on the black indicator and the Hispanic indicator, we get precisely those numbers, or well, within rounding we do. Okay, so the coefficient on the indicator for black non-Hispanic is 17,461. That's this number here, which corresponds to the difference in these two means. And for Hispanics, it's the difference between Hispanics and whites, right? So whites, the mean value of income when black, the black indicator is 0 and the Hispanic indicator is 0, is simply the constant, right? And that's the mean value for white, which is shown right here. Okay, so regression gives you the mean difference between the indicator taking a value of 1 and the omitted category, which shows up in the constant. Okay, it's there, it just shows up in the constant. Okay, so let's say we leave one of these indicators out. Let's say we want to look at for some reason, we want to look at the difference between whites and everybody else. Then we would just, in this case, we can just use the table command, which we just say table white, that's our row variable, comma C for contents, mean income, N income, okay, and that gives us the mean income for non-whites and whites, right? So 56,403 is what we got up here, okay, and then the average income for blacks and Hispanics pooled together is 45,739. But as we can see, the incomes shown by our in NLSY are quite different for Hispanics and blacks, so there's really no point in pooling them together. But let's say we ran a regression of income on white. Now the coefficient on white means something different than when we had the regression of income on black and Hispanic, obviously, right? So now the coefficient on white is the mean difference between whites and blacks and Hispanics pooled together, right? So the mean for blacks and Hispanics pooled together is 45,739. The mean difference between non-whites and whites is 10,664, and that's what shows up right there. So going back to our do file, I want to call attention to this code right here. This code gives you a shortcut way to include indicator variables. Okay, so this is called factor notation in Stata. And if we enter a multinomial variable like race ethnicity, which has no order to it, so we wouldn't want to just include it the normal way, like a continuous variable. If we use factor notation and declare it as a multinomial variable or a categorical variable, we just include I dot as a prefix to the variable name. Okay, and then we can use the margins command afterwards to get the predicted margins, the predicted fitted values for income given those predictors. Okay, so let's try that. Just highlight that, run it, go back to our do file. Okay, so now we get the same results as before. It's just a little more convenient to say I dot race. And we get our mean differences. In this case, Stata left out white as the base category. Stata will by default leave out the lowest value in the variable, which in this case is 1. So that's the white category, and then the mean differences between whites and blacks are shown here. Okay, and then we can just type margins, race, ethnicity, and it will give us the mean values of income, which in this case are the same thing that we would get if we used the table command. Going back to our program now, we can look at these two lines of code. Okay, this is where margins really comes in handy, because if we type regress income I.race, okay, that'll include the two dummy variables or the two indicator variables for Hispanic and black, and then we can adjust for math test score. Then our predicted margins will be predicted mean differences controlling for test score. Okay, so let's run that. And we'll go back to our results. And now the results are slightly different, or they're substantially different, because now these mean differences adjust for a young adult's test score that they received in 1997. So the coefficient on math test scores, the way we'd interpret that is a 1 unit change in math test score. I think in this case it's percentile, so a 1% change, or 1 percentile change in this test score is predicted to net a student $129, controlling for their race and ethnicity. And just because white isn't shown here, whites, it's the same adjusted effect for whites. Okay, whites are now in the constant. Okay, so with margins, these margins now are predicted means adjusted for the effects of test scores. So this is comparing, this is the predicted mean for whites controlling for test score. This is the predicted mean for blacks controlling for test score, and the predicted mean for Hispanics. So notice the black predicted mean comes up substantially. So if you compare whites and blacks with the same test score, there's still a gap, but the gap isn't as large. Okay, the remaining parts of the code here are two different ways to estimate an interaction, a binary by continuous interaction term. Okay, we're going to go through each step, how to calculate it, how to do it the old school way, and how to do it the new school way. So first we just generate an interaction term, which is the multiplication of two variables. In this case, it's black times the math test score. And so we just say gen, we give it a name. I'm giving it the name black times math equals black underscore non-Hispanic. That's the name of the variable times the math test score variable name. We do the same thing for Hispanic. Okay, and then we run a regression with two interaction terms, one for black, one for Hispanic. Okay, and we include the main effects. The main effects are the terms upon which the interactions are based. Okay, so in this case, it's the black indicator variable, the Hispanic indicator variable, the math test score, and then the two interaction terms. Okay, we can also do this with factor notation. This is the new school way to do it. We say I.race #, C.math score, basically the math variable name. Okay, and this tells its data to include the main effects and then the interaction of the two variables for all the different categories. Okay, and then we can type after that margins for race ethnicity, the categorical variable, at certain values of the math PLCY score, going from 0 in increments of 10 to 100. Okay, then we actually plot the data. All right, so let's run that and take a look at it. Okay, when we get our results here, we regress income on the indicator variable for black, the indicator variable for Hispanic, test score, and then the two interaction terms. We can look at the effect of the test score. That's the effect of the test score for whites because they're the omitted category. And then we can see that if someone is black, the effect of test score is actually 75 plus 118 for blacks. So the slope is steeper for blacks. And then for Hispanics, it's also steeper. Okay, the slope for Hispanics is 75 plus 105. Okay, both terms are statistically significant. Okay, and if we do it the old school way, it's less coding on our part, but we get the same results. Okay, and then we can do our predictive margins and look at a graph, which in this case shows that for blacks and Hispanics, the slope is steeper for each increment of PIAT math score. That's the end of the tutorial.